Looking to section 2.3, we're going to look at some terminology of the periodic table. So looking at what are periods, what are groups, know how to use information given to us on the periodic table, and then look at some similarities and some differences and properties of some common elements in groups. So elements were first arranged by increasing atomic number. So as we look from left to right across the periodic table, we can see that numbers get bigger. As we look from top to bottom, numbers get bigger. The periodic table was arranged before electron configurations of elements were known, and we're going to get into electron configurations here in later chapters. But the properties of elements are periodic. Dmitry Mendeleev and Mayer were both scientists that helped arrange and put together the periodic table. Dmitry Mendeleev, one of the founding fathers of putting together this periodic table. One thing he is especially known for is after putting together the periodic table, he left holes where he thought an element should be, but yet hadn't been discovered yet. So this particular element, germanium, he knew about gallium and arsenic, and he knew about silicon and tin. So if you look at the periodic table, germanium is right in between those. And so he looked at properties of the elements that are to the left and to the right of it, and above it and below it. And so back in 1871, he predicted that the atomic weight of this hole, this gap, would be around 72. And it is about found in this element that was found in 1886. So 15 years later, they said, yeah, there's this element with an atomic weight of 72.59. He predicted that the density of it would be 5.5, and it was 5.35. He predicted the specific heat, very close, that it had a high melting point. He predicted the color of it, what formula it would be when formed with oxygen, the density of that compound, a formula if it formed with chlorine, which he was accurate, the density of that compound, and the boiling point of that compound. And again, this element here, germanium, was found 15 years later, and he was so close to having all those similar properties. So the periodic table, what do we know? How was it arranged? Well, there are periods, there are rows, there's metals, nonmetals, metalloids, there's halogens, noble gases, alkali metals, there's electron configurations, blocks that has s, p, d, and f electrons. Again, we get into that in later chapters. There's lanthanide and actinide series. So much we can see and look at with the periodic table. So we've got these columns or groups. Notice we have our A groups, and then we have our B groups. These A groups are our main groups, or families, we can call them. We have over here, number 8, these are our noble gas family. This is our noble gases in that 8th column. In the 7th column, those are our halogens. I'll just say H's. Over here, A1, those are our alkali metals. Number 2 is alkaline earth metals. So those are some common groups. The B group are not our main group. These are our transition metals, our Bs. And then we have our periods. Our periods are the rows. And if you look at the periodic table, there are 7 rows. Even if you look down below the inner transitions, notice they still are rows, part of row 6 and row 7. So these are our periods. Our periods are the rows. So take a second here. Let's see if you can answer this one. Which list of elements include those in the same group? Why don't you pause here? Did you get boron, aluminum, and thallium? What about this one? Which list of elements include those in the same period or row of the periodic table? Hopefully you got iron, cobalt, and nickel. Which element is an alkaline earth metal? That would be calcium. Already moving on to section 2.4. We are going to look at recognize, interpret molecular formulas, condensed formulas, and structural formulas. We're going to look at the formulas and names of common molecular compounds, and then we're going to write and name formulas of binary molecular compounds. Okay, let's refresh. Compounds and molecules. Compounds are any combination of two or more elements in definite ratios. The character of each element is lost when it's formed in a compound. For example, hydrogen and oxygen have very different properties when they are by themselves compared to when they are in a compound and it forms water, H2O. So yes, I still have hydrogen and oxygen gas in a fixed ratio. There's always two H's and one O, even though we don't put that one is implied that it's there, in water, or dihydrogen monoxide. Now, molecules are the smallest unit of a compound that retain the characteristics of the compound. So nonmetal combined with a nonmetal. So this would be a water molecule, right? Two nonmetals combined, and it cannot be reduced anymore. The ratio of 2 to 1 cannot be reduced. Let's look at, for example, ethanol versus dimethyl ether. This molecular formula, we've got 2 carbons, 6 H's, and 1 O. That's its molecular formula. So telling me its ratio of carbons, hydrogens, and oxygens. It's 2, 6, 1. Now the condensed formula, we can see here, CH3, CH2OH. That's kind of telling me what its structural formula looks like. So there's the C, there's a H3, 1, 2, 3. So there's that first part. Then CH2, there's a C, 2 H's, and then an O and an H, O and an H. So this condensed formula is going to show me the order that structural formula is going to look like. And then we have this molecular models. What does it actually look like in 3 dimensions? Here we've got our dimethyl ether. And we can see here the molecular formula. This tells me that ratio 2, 6, 1. The condensed formula, notice though, is different. So it's the same molecular formula, notice, but it's arranged differently. Its condensed formula is differently. This says CH3, so the beginning part is the same. CH3, CH3, so that first C, HHH is the same, but then it tells me O, right there, and then another CH3, CHHH. So notice the condensed formulas are different, which makes its structural formula different. And then it's going to look differently three-dimensionally. Using models is just a way to represent so we can see three-dimensionally what methane looks like, CH4, so 1 carbon and 4 hydrogens. And drawing it is tricky because obviously if we draw something it's 2 dimensions. But we can see here, if I draw my carbon here, we can have 1 hydrogen kind of sticking up, like this guy is sticking up. And then if there was 3 other hydrogens, it's kind of making a little TP or a pyramid in your hand. And so we kind of show that by 1 over here, 1 coming at you, and 1 kind of going behind you with these dashed lines and a little triangle. Ball and stick model, that's another way to represent. A space filling model is another way to represent. So all different ways of showing the same molecule. Let's look at the chemical equation here. So we can use a word description to represent this chemical equation by saying methane or carbon tetrahydride, we'll get into naming here in just a minute, reacts with, that means plus, oxygen, O2. O2 is always diatomic by itself. We're going to Brinkelhoff, B-R-I-N-C-L, Brinkelhoff. Anytime any of these elements, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, Brinkelhoff, anytime any of those elements are by themselves, they are always diatomic. Okay, it says it yields Yields is an arrow. That means it combines to create carbon dioxide and water, CO2 and H2O. So this is our symbolic representation of a chemical reaction. We have our reactants on our left, our products on our right. We can also include more details if we include the states of matter. And that's telling me if I have gases or liquids or S for solid. An AQ is an aqueous form. So that would be like if I dissolved salt in water, I would have sodium chloride solution. And so I would say that's aqueous. So if it's in solution. Okay, now let's get into naming. When nonmetals combine, they form molecules. They may do so in multiple forms. Now, CO, I would name carbon monoxide. So we have to tell you, when we have molecular compounds, we have to use prefixes. These guys, we have to use 1 through 10. The only time I do not use a prefix when I have a molecular compound is when I have one of the first element. So I need to look at this compound, and first of all, I need to say, are they two nonmetals? Carbon and oxygen? Yes. Okay, there's one carbon, so I just say carbon. But I do need to say that I have one oxygen, so I would say monoxide. And that monoxide, the O's smushed together, monoxide. Okay, now here, CO2, I have one carbon, so I'm just going to say carbon. But I do need to say that I have two, or dioxide. The ending of the second element always turns to "ide." Let's look at these examples. There's one boron, so I'm just going to say boron. Boron's a nonmetal. Now you might look at your periodic table and it says M and it says it's a metalloid. Listen, if it's not a metal, metalloid is not a metal. So we still count it as a molecular compound. And then I need to say 3 chlorines, so trichloride. 1 sulfur, so just sulfur. 3 oxygens, trioxide. 1 N, nitrogen. 1 O, monoxide. I'm not going to say mononitrogen, just nitrogen. This guy, I have 2 N's, so I do need to say dinitrogen. And then 4 O's, tetraoxide. Okay, pause the video here, see if you can write carbon tetrachloride. Hopefully you got CCl4. Can you write sulfur dioxide? SO2. Can you write silicon hexabromide? Pause. SiBr6. What about diphosphorus pentaoxide or pentaoxide? Pause the video. Hopefully you got P2O5. All right. The molecule whose structural formula is pictured below is one of the essential amino acids. What is the molecular formula of the acid? Pause the video here. See if you can figure that out. Did you get C3H7NO2? And that's just the molecular formula is looking at that, just adding up all of the carbons. That's my ratio. So I got to add up 1, 2, 3 carbons, and so on. How about this one? What is the molecular formula of saccharin, which is an artificial sweetener? Hopefully you got C7H5NO3S. All right, great job.